Okay, let's try this analytical geometry. The first question says determine the lengths of AB and AD. Well, all we use is the distance formula, and I like to use the distance formula without the square root thing. So I figure out what AB squared is. I subtract the two x values, 4 minus minus 4, which is 4 plus 4. I square it and then subtract the two y values. 4 minus minus 2 is 4 plus 2. And I get that is 8 squared, which is 64. That's 6 squared, which is 36. It equals 100. And I square root both sides at the end, and I get AB equals 10. Well, I do exactly the same thing with AD. I go minus 7, minus minus 4, 2 minus minus 2. I get minus 3, which is squared, which is 9, 4 squared, which is 16, 25, square root it, 80 is 5. Now, what are the coordinates of M, the midpoint of B and D? Well, all you do is add the x values and divide by 2. So that's minus 3 halves, negative 7 plus 4. 2 plus 4 divided by 2, that's the y coordinate. Add the y coordinates and divide by 2, and you get 3. It's the average of the x coordinate. Two things added together divided by 2. You find out what's in the middle of any two numbers. And it works for the x coordinates and the y coordinates. Determine the gradient of AB. Well, there's A, there's B. We've already done the work over here. Here's the change in x is 8. The change in y is 6. So 6 divided by 8 reduced is 3 over 4. That's the gradient of AB. The change in y over the change in x. Subtract the y's and subtract the x's, and we already did the work in the first question. Prove that AB is perpendicular to AD. Well, if they're perpendicular, the two gradients need to multiply to equal negative 1. We know the gradient of AB is 3 over 4, so all we have to do is figure out the gradient of AD. And we've done that work. There's the change in y, which is 4. There's the change in x, which is minus 3. And minus 4 over 3, well, that means minus 4 over 3 times 3 over 4, that equals negative 1. Therefore, AD is perpendicular to AB because the product of their gradients is equal to negative 1. And there you go, all done.